Good evening once more. Today we'll be discussing chi-square distribution. We'll continue our discussion on continuous probability distribution. So the day before yesterday, we discussed normal distribution as a type of continuous probability distribution. Today we want to discuss chi-square distribution. I want to start with a historical perspective. Pearson in London, or in some years in London, was considered the founder of mathematical statistics. He developed the chi-square test and published it in 1900. That's more than a century ago. He coined the term standard deviation. He developed the product moment correlation, even though it was his teacher, Gattin, that first of all talked about moment correlation, where he developed it. So for some of us that were in the lecture, or you have listened to the lecture on correlation, how correlation was derived from covariance. It was Pearson that first discussed that, and now this is Pearson. He was a geneticist. Let's quickly talk about how he was the first to discuss Pearson correlation. And apart from Pearson correlation, the first to discuss chi-square. And that is why the commonest chi-square is named after him, Pearson chi-square. Now, we first of all look at standard normal distribution that we discussed 2 days ago. We discussed this normal distribution and standard normal distribution as a continuous probability distribution. Now, it will interest you to know that chi-square is like an offshoot. So what Pearson did was to do something to normal distribution to now get chi-square distribution. What did he do? Now, before you look at what he did, as an overview, you remember standard normal distribution, the mean is 0, and the standard deviation is 1. We discussed that 2 days ago. And because it is bilaterally symmetrical, 1/2 of the graph, that if you show it as a probability density function or mass function, 1/2 is the mirror image of the other half. That is, it is bilaterally symmetrical. So the mean is 0. That shows that towards the left of the 0, you have negative value. Those are the values that are below the mean. In the real life, if let's say the mean is 17, so the real value of those ones that have standard deviation of minus, z-score of minus, mean that they are below the mean, because the mean coincides with the mean of which is 0 here. So anything that have positive value, those are the value above the mean. So the fact there is that the normal distribution have 2 sides. One side negative, on the left side of the 0 negative, the right side to the 0 positive. And from there, don't mind the graph you see now, it touches the, normally it goes to infinity on both sides, negative and positive side to infinity. So what, if you remember how we got the standard normal distribution, it's just to remove x, mean, the population, from the individual value, which is x, and divide by the standard deviation population, it gives you the z-score, which is z. Now, what did this man do, Pearson? What he did was to square the z. If you square z, that is, if you square normal distribution, it gives you chi-square distribution. So the word chi is from Greek letter. But when you say chi-square, it just tells you that that was the origin. Squaring normal distribution give you chi-square distribution. If you look at the normal distribution we just look at, if you look at it, the majority, the mode is at the zero. The majority of the graph concentrated around the zero in the middle. As you move away from the middle, the frequency drop on both sides. That's why the graph goes down on both sides. So if you square, what is the implication? The implication is that all these negative value you see that go on this left side of zero will become positive, because anything negative times negative will become positive. So chi-square does not have negative value, unlike standard normal distribution that has negative value. When you square the standard normal distribution, all the negative value become positive. So that is one implication. As you can see, you see now, the chi-square now, there's nothing to the left of the negative. That is one. Two, you will see that the middle for the T normal distribution, the middle around that zero, that's the peak of the graph. And from there, going above or going below, the frequency goes down. That is the number of observation, number of people on observation that have those frequency go down, that have those values go down. But when you square it, it gives you chi-square distribution. What will happen is that immediately after that zero, it will peak. The reason is very simple. You know that most of those values in normal distribution, and most of them concentrate around that zero. So when you square now, both those ones that are negative or positive, all of them become positive. Now, because in normal distribution, most of them peak around that zero, either from the negative side or the immediate negative side or immediate positive side. So when you now square, now since all of them become positive, so immediately after zero here, it will peak because those values will be there. It now begin to slack. So that is why chi-square will peak and now begin to go down. And so you can see that it is now skewed. It's skewed to the right. It's not to the left because it's skewed to the right. So no negative value. The mean is equal to the degree of freedom. The standard deviation increases as the degree of freedom increases. We'll talk about it because I don't know how many of us that have watched listened to the video on the degrees of freedom. Very, very important. But many people, we ask them to go and listen, they won't listen. But it's even free that you can go and watch. There are some of those videos that are on the YouTube without you subscribe directly. All of them are on YouTube. But you can access some of it directly. Just type through the laptop, YouTube, you get it. You can subscribe to that one without payment. But it is not all the videos are there. I think that one should be there on the degree of freedom. But all those other ones about other things, they are not there. So there are some things that are there, there are some that are not there. If you want to get everything, just subscribe, you get everything through our website. But you can still listen to watch some of them just by even without going to our website, just type my name, YouTube, you will get some of this video. Now, you will see that the chi-square, one thing you will know, apart from the fact that it doesn't have no negative value, and it's skewed, there are some important facts you need to know about chi-square. Of course, it is not symmetrical, that's why it is skewed. It's from 0 to infinity, no negative value. Whereas normal distribution is from 0 to infinity on both sides. But here is from 0 to infinity on one side, no negative value. It's skewed to the right. But just like normal, not like any probability distribution, the total area is 1. Cannot be more than 1. Probability cannot be more than 1. So any either F test, T test, chi-square test, think of any test in any distribution rather, F distribution, T distribution, chi-square distribution, normal distribution, even all those discrete probability distribution, the area is 1. The total area is 1. Probability cannot be more than 1. So is one thing I want you to know here is a family distribution. Unlike, if you remember, when we talked about normal distribution 2 days ago, we said that if you try to plot normal distribution for each variable, they will give you different, each variable has its own normal distribution. I mean, each variable that is normally distributed has its own normal distribution. And that's why intelligent people have to know we want only one. If you want only one, you now convert each value to Z-score. You convert to Z-score by just removing the mean, the population from each value and divide by the standard deviation of the population. It gives you the Z-score. And that's what gives us the standard normal distribution, which the mean is 0 and the standard deviation. And the area under the graph is 1. So this one also, the area under the graph is 1, but it's not one distribution like standard normal distribution, which is 1 and is universal. This is a family distribution. It says that there are different types based on the degree of freedom. It's a family distribution. That is, you have different shape of chi-square depending on the degree of freedom. And the degree of freedom is not totally dependent on the, in fact, it's not even maybe, it's not dependent, that one is not dependent on sample size, it's dependent on the contingency, the category, number of category rather, let's say, so that you can understand. Because the contingency is just when you cross-tabulate 2 variables, you are merging 2 categories at the same time, 2 different directions. That's contingent, but number of categories. So number of categories, you know, the chi-square distribution is actually used to explain the sampling distribution, the distribution of categorical variable, because it is used for categorical variable. Even though the categorical variable does not follow normal distribution, but their sampling distribution will follow normal distribution. So now, for chi-square is not actually, though sometimes the number of categories may be determined by the number of, by the sample size, but the degree of freedom does not depend on the sample size, unlike for T and F, where the degree of freedom depends on the sample size. But this one, the degree of freedom depends on the category. I think in one of the lectures where we talk about, that lecture we talk about understanding statistics beyond the basic concept. We talk about at least something about degrees of freedom, at the category -1. So it's a family distribution that the shape depends, you get different shape depending on degree of freedom. If the degree of freedom is 1, the shape will be different, it is 2, 3, 4, 5, like that. But as the degree of freedom increases, it begins to look like normal distribution. Okay. This one just to illustrate, this one just to give a clue about the way the degree of freedom is calculated in chi-square distribution. So how you get the distribution, you know, if you are relating to variable, categorical variable, one will be, if you cross-tabulate them, one will be on the horizontal, one will be on the vertical. So the one in the horizontal, the degree of freedom will be number of row -1. The one in the vertical, the degree of freedom will be number of column -1. Like this one, this first one now, there are 2 row, 2 column. We are talking of the green part because we are not, when you are talking of row and column, total is not part of it. Total is at the edge. We are talking of the one that contains the data set apart from the total. So like for this one, this is 2 by 2 contingency. The degree of freedom is 1 because there are 2 row, 2 column. 2 minus 1 times 2 minus 1, making 1 times 1. For this one now, the degree of freedom for this one, we have 3 row and 4 row and 3 column. So the degree of freedom for the row will be number of row 4 minus 1, making 3. For the column is 3 minus 1, making 2. 3 times 2 is 6. So for this one is 6. So when we talk about cross-tabulation, when we arrange a table in row and column, call it cross-tabulation or cross-tab or two-way table. Now, Apart from I will still show us the different, how you arrive at different degree of freedom, and the shape of the chi-square with different degree of freedom. But before we do that, if you have your question, please type. Apart from the fact that chi-square distribution, as you see it, is a family distribution in the sense that it depends on the shape of the distribution, depends on the degree of freedom. The different scenarios follow chi-square distribution. How will you put? Do we call it type of chi-square statistic now? That means different statistics that follow chi-square distribution. In fact, it's uncountable. It's only the one anybody knows that you will tell you. You just listed this one now, maybe about 9 here, but it's more than that. The commonest one, Pearson chi-square distribution, is what? That's the first to be, it was Pearson that first described chi-square. So the commonest one is called Pearson chi-square. When you are comparing two categorical variables, you use it. Likelihood ratio chi-square, the same thing, doing the same thing with the Pearson chi-square, but it's just different way of arriving at it. The same chi-square. McNemer or McNemer-Barker, when you are talking of proportion of peer observation, and we have chi-square for trend. If you have an outcome that is two category better, exposure is ordinal. Like maybe you want to know how many are employed among different socioeconomic class. You see different employed, not employed, that's the outcome, but the different socioeconomic class will be upper, middle, lower. So you cannot have ordinal variable unless you are having up to 3 categories of it. So we know that upper is higher than middle, and middle is higher than lower. Mantel-Hampson chi-square for stratified analysis. All of them, they follow chi-square. What statistics follow chi-square? Using logistic regression. Kuka-Wallis statistic is for parametric counterpart of ANOVA. One way ANOVA is chi-square. There are many things. Log-rank statistic for comparing Kaplan-Meier survival curve follow chi-square. I think there is one that is hiding under that place. So we have different statistics that, yes, chi-square for heterogeneity, that's for meta-analysis. We are going to, in 2 weeks time, we're going to do meta-analysis workshop. It's chi-square. So we have many things that follow chi-square. Just a minute, just 1 minute. Sorry, I'm back. So those are the different statistics that follow normal distribution and that follow chi-square distribution. Now, the issue of the degree of freedom, just to conceptualize again, when you are talking of degree of freedom for quantitative variable is number in a sample, the sample size minus 1. But for categorical variable, the number of category of outcome of that variable minus 1. But when you look at association between two categorical variables, you have to calculate the degree of freedom. The degree of freedom will be for this one times this. The degree of freedom for the one category and for one variable times the degree of freedom for the other variable. Like for the one we have just said, and the degree of freedom here is 1. Is a number that cannot vary. So just this one, I just try to run through it because today is not for the degree of freedom per se, because we have different lectures that we have given on degree of freedom. Think on to increase yourself. There you can really understand. If you can see the red, this one just showing, this red is just showing out of these 4 cells, only one can be, the degree of freedom is 1. Because if you look at the row, there are 2 rows, you remove one from it, remain 1. The column that are two columns, so 1 times 1 is equal to 1. So even with the diagram, the degree of freedom is 1. For this one that has 6 sets, the degree of freedom is 2. And if you look at it also, number of row, 3 row minus 1 making 2. Number of column, 2 column minus 1 making 1. 1 times 2 is equal to 2. Here, the same thing also here. 2 times 1 is equal to 2. The degree of freedom is equal to 4 here. And what will warrant the degree of freedom being 4? In all these 3 scenarios, the degree of freedom is 4. Different scenario. This is 3 by 3. This is 3 by 3. The row is 3, column is 3. The 3 minus 1, 2. 3 row minus 1, 2. 2 times 2, 4. Can you see? In this one that we have 5 row and 2 column. The degree of freedom is 4 also. Because you remove 1 from 5 is 4. Remove 1 from 2 is 1. 1 times 4, 4. This one that has almost like the other one also, just in opposite direction. 5 column, 2 row, the degree of freedom is 4. This one, the degree of freedom is 5. There are 2 scenarios here. You have 2 row, 6 column. Here you have 6 row, 2 column. It's the same. Here the degree of freedom is 6. There are 6 scenarios, 4 scenarios. 3 row, 4 row, 3 column. That would be 4 minus 1, 3. 3 minus 2, 3 minus 1, 2. 2 times 3 is 6. Or in this case, where you have 3 row, 4 column, still 6. Or you have 6 row, or 7 row rather, 7 row, 2 row, 7 column, or 7 row, 2 column, and so on like that. So this is the shape of chi-square. Can you see for this different degree of freedom? The one that has the degree of freedom of 1, this is the shape. The one that has 2, this is the shape. This is brown one. The one that has 3, this is the shape. This is blue. The one that has 5, this is green shape. The one that has 10. You will see as the degree of freedom increase, the shape is looking like normal distribution. Look at this one. So when it's 5, when it is 10, when it is 15. So as the degree of freedom is increasing, the shape look like normal distribution. So it will interest you that it's not only chi-square that behave like that. By next week when we talk about T distribution, F distribution, as their degree of freedom increase, they become like chi-square and normal distribution. So you see, just like the question that somebody asked 2 days ago, we wanted to know this normal distribution, is it the normal variable that follow normal distribution or sampling distribution? It's both. It's only normal distribution that has that. All this other one is there's no natural variable that the value follow normal distribution. It has to be a statistic, a sampling distribution. It has to be summary of group of sample. Like chi-square now, you just have to have the sample to calculate chi-square. The same thing with t-test, T distribution. The same thing with F. That one is ANOVA. You are having many groups, but the issue is that you have more than one person, subject. Same thing for all of them. But for Z, it can be the same for Z best. See, you can calculate the Z for each value, for each person. You can calculate your Z for your height, or your blood sugar, for your distance, and plot it. For everybody, just calculate the Z. So it doesn't have to be group. So you can see it's only Z distribution, which is normal distribution, standard normal distribution. That is like a natural, the most variable that follow normal distribution, they naturally follow it. Then all these other one, they are not, there's no one variable that will follow it. That will be the statistic you get from those variables that will follow normal distribution, that will not follow this distribution. And when the sample size, in some cases, increase, that make the degree of freedom to increase, or whichever way, when the sample size or sometimes the category, number of the category you are dealing with increase for the chi-square, the degree of freedom will increase, that distribution will become like normal distribution. So normal distribution is like the one that is a physical. But this other one, they are under normal, they are hiding. It's something that will bring them out. So a lot of phenomena are hiding under that. So that is just, look at this now. For different degree of freedom, also just try to show the. So I will not talk more about the significant level, because it's when we talk about the hypothesis testing, we want to talk about that. Though if you go and listen to the lecture on introduction to inferential statistics, where we talk about the sampling distribution, hypothesis testing, and central limit theorem, we talk about them here. But just know, can you see the shape? So different degree of freedom. And the only thing I can see here, if you remember normal distribution, we talk about the middle 95%, which correspond with 1.96. But that same normal distribution, that middle 95, it means that you are putting the middle, that 95% is in the middle. If it's one side, that's 2T. If it's one side, if that 95% is in one side, in that case, we are going to have 95% on one side, and we're going to have 5% on one side. In that case, it will not be 1.96 to 1.64. Look at this one, chi-square now. This chi-square now. 3 for the degree of freedom of 1. This blue, this chi-square is 1 for the degree of freedom of 1. The area, the critical value that separates 95% of because the total area is 100%. The value that separates 95% from 5% is 3.84. And you see, chi-square 3.84 for the degree of freedom of 1, the one that separates 95% of the area from 5% of the area. But if you come to the degree of freedom, other degree of freedom, you're going to see that it's not the same value that separates 95. Like for this one, the degree of freedom, I think this one is degree of freedom of is 6, yes. This last one is degree of freedom of 6. The value is 12.23 that separates the 95% area from the remaining 5%. 12.23. I think we stop here. Okay, before that one, this is just a table that show, I told you that for continuous probability distribution, you cannot show it on the table. You can only show it in a graph. This table is not actually showing, this graph here is showing continuous probability distribution, but the table is not showing continuous probability distribution for chi-square. It's just showing the critical value, where the critical value that separates, the value that separates 95 from 5%. And for 1T or 2T, either the middle 95 or one side 95 is showing, look at it, like this one, and the blue part you are seeing is telling you that is, okay, everything here is even 1T. The blue part now is the proportion, can you see, which is the blue, light blue, sky blue, while the dark blue part is the proportion that is the 5% side. So for the different degree of freedom, can you see, for different degree of freedom, 1, 2, 3, 4, 5, like that down, it's trying to tell you the area under the curve and the value that separates them. So this, for example, now, for degree of freedom of 1, which we said the other time, for 95% confidence level, which if you separate 90, you remove 95, it remains 5%. Can you see? Yeah, 3.84, 95, 5. If it is 90%, when you remove 90, it becomes 10%, it remains 10%. This is the value. If you are talking of 99%, it remains 1%. So that is why it is said that though this one is applicable to any form of distribution, the level of significance if plus the level of confidence make 100. So I think we stop here because just for you to have a glance about how chi-square distribution was gotten, the origin, how it originated from chi-square distribution, and some similarities, some differences. So I don't know if there's any question. They will be surprised there is no question, because sometimes when you just say no question, you will see that it's either that you understand everything or everything is not clear. But I see that every day you understand everything. So any question from any angle? Any question? So it's very simple. So if you cannot ask, you can chat it. Can chat it privately. There's no question that's stupid anyway. But
okay.
Okay, go on.
Thank you very much for the we're looking at a journal in my department last week,
okay,
and we had a table that showed a chi-square value of 5.588 and a p-value 0.02 or so. That chi-square value 5.588, how do we interpret it, or is it needed?
Yes, from what you have just said now, the chi-square value of 5 point something and the p-value is 0.02, it shows that it's significant. It shows that the degree of freedom is 1. So let me just show you. Let me go back to what we just did now. For me, from that, everybody will know that the degree of freedom for that chi-square, for that scenario, let's say the scenario, the degree of freedom is 1. So how do I know that? From what we have just discussed, you know, this value, this is the critical value, 3.84. For the degree of freedom of 1, the critical value is 3.84. For 95, because most of the research we are doing, they use 95% confidence level, and the level of significance will be 0.05. You know, 95%, which is 0.95, plus the level of significance, which is 0.05, making 1 or 100. 95 plus 5%, making 100%, or 0.95 plus 0.05, making 1. You get it? So your level of confidence and your level of significance, they are equal to 1. If let's say they have chosen 99%, the critical value will be 0.01. Exactly. So now, most research use 95% confidence level and 0.05. Of course, if you say 95%, that shows that your level of significance is 5%, which is 0.05. So the critical value for chi-square for that is 3.84. Can you see? So for the 3.45, if you look at the 5 something, is more than 3.84. So once the chi-square is higher than the critical value, the p-value will be lower than 0.05 because they move in opposite direction. And I made mention of that also, was it last 2 weeks? The statistics, as they move in one direction, the p-value moves in the opposite direction. It's only a group, Wilkinson and McWhitney-U that differ. Wilkinson and McWhitney-U, which are non-parametric counterparts of t-tail, they are the one that differ. As their value increases, also the p-value increases. So in that case, for it to be significant, you have to have lower value for those statistics. For other statistics in hypothesis testing, for it to be significant, you need higher value that is greater than the critical value. Let's say now, if let's say it was degree of freedom 2, that 5, well, it depends. If it's 5.8 something, it will not be significant. It will take 5.99y. Can you see? For degree of freedom 2, it will take 5.991. For that 95% and 5% will be significant. If it's degree of freedom 3, it will be 7.815. So sometimes you see chi-square that is 7 point something is not significant, whereas you see the one that is 4 point something is significant. The only difference is that both of them, they don't have the same degree of freedom. Maybe the one that is 4 point something that is significant because the degree of freedom is 1. maybe the one that is 7 point something, the degree of freedom maybe is 4, 3. So for 3, is that would be above or equal to 7.815. Can you see as the degree of freedom increases, the required sample size chi-square for it to be significant increases also. So the interpretation of that result is that it's significant. What you are using to, they might have used it to compare, to look at association between two categorical variables. It's telling you that there's a significant association between the two categorical variables. So the two categorical variables now, the interpretation now depends on the way you do this and table and put the percentage. You can have something that is significant, good work like that, but you misinterpret because you don't know how to put percentage. Somebody called me yesterday so that we send me text yesterday or call. We discuss this issue, the direction of percentage. You can know because you must know which one is outcome, which one is exposure variable, and we have to clarify those issues. So that's why in our workshop, that's why we talk about beyond lecture. We stay the workshop for you to hand on. You run the analysis together. We look at you. We ask you to do this. You run it. We look at the result, how to tabulate the result. So I don't know if I have answered your question because I have talked much about this. Okay. Yes. Any other question? Okay. Any other one? So no other question. Okay. So it's so clear. If that's the case.